Log on, tune in, find out. Another good idea from Cambridge.
Visiting us for about 6 weeks actually. Been great having him around. And this afternoon he's going to talk to us about Gromov's theorem on groups of polynomial growth.
Okay, thanks Ben. Nice to be here. So I was initially, as the title says, going to talk about mostly about Gromov's theorem and how it's proven. But I decided actually to give a slightly more broader, touchy-feely, high-level talk, in which with less proofs, but it's just sort of more the general big picture. And so I won't actually prove any theorems, but you actually see some bits and pieces of proofs sort of floating around in what I'll be doing. So I'll be talking about Gromov's theorem as part of a family of wider theorems, which seem to illustrate this sort of general principle, which I don't know, sort of Gromov type principle, I guess. Right? So I'm going to list a bunch of theorems which illustrate the following principle: that every time you have an object of controlled growth, okay, so an object of controlled growth this always seems to whenever you have an object that grows in a very controlled manner, an algebraic object like a group, then it tends to always come with some sort of a Lie structure, or actually more precisely virtual Lie structure. So it basically looks like a Lie group up to some bounded index in a continuous, if it's a continuous object. And if it's a discrete object, then you get something a little bit better. You get virtually an important structure. In a discrete case. So there's now a bunch of theorems that sort of exhibit this principle, and so there seems to be something going on here, that every time you have some sort of metric type of control on a group, you tend to get also a lot of Lie or algebraic type control on your group as well. And we're just beginning to understand exactly why this is the case. So let me list some theorems that exhibit these sort of principles. So the first one is indeed Gromov's theorem. Which says that every finitely generated group of polynomial growth is virtually nilpotent. So let me give some definitions. Okay, so finitely generated group, so it's just a group with some multiplication operation with some finite generated by some finite set S. Generators. Once you have a set of generators, you can define the balls. Put it over here. So you can define the ball of radius r to be the set of all words formed by S. Let's say S is symmetric. So you take all the words of length at most r. That's just the ball in the word metric of length r. So that's a finite set. It has some cardinality. It will grow at most exponentially in R because if S is finite. But we say that we have polynomial growth if the growth here is bounded by some polynomial in R for all R. Okay, that's what it means to be polynomial growth. Okay, so some groups are polynomial growth, some groups are not. So examples of, so this is the polynomial growth condition. Okay, so examples of groups that are polynomial growth are abelian groups. Finitely generated abelian groups, such as, for example, Z to the D. Balls in Z to the D grow like R to the D. By the way, you can check that it doesn't matter exactly which choice of generators you pick. If you pick a different set of generators, you get the same growth asymptotically, so that's not so important. But yeah, so an abelian group which is finitely generated has polynomial growth. More generally, an nilpotent group. So it's a group which this has a central series of abelian extensions, central extensions, also has polynomial growth. A good example is the Heisenberg group. Of these upper triangular matrices here, where the entries here are integers. So this is a no-potent finitely generated group. It has generators 1, 1, 0. So it's generated by 2 elements. Finitely generated. If you take a ball of radius r, if you take products of r of these matrices and the inverses, you'll get a matrix which, if you do the matrix multiplication, looks something like this. If you multiply these two matrices together r times, you get a matrix where these entries will be of size about r, and this entry will be of size about r squared. So there's about r to the 4 elements here, so this is a group of polynomial growth. And more generally, you can show by induction that every no-potent finitely generated group has polynomial growth. Another sort of trivial example of a group of polynomial growth is a finite group, because the balls just expand to fill the group and then they stop. So clearly that is a group of polynomial growth. And you can combine these two to get a virtually no-potent group, as an example. So a virtually no-potent group is a group which has a finite index subgroup, which is no-potent. And once you know that finite groups and no-potent groups have polynomial growth, it's easy to see that virtually no-potent groups also have polynomial growth as well. And Gromov's theorem is the converse, that these are the only groups of polynomial growth. Okay. So, for example, if the free group certainly does not have free non-abelian group on, say, 2 generators, certainly it does not have polynomial growth, it's exponential growth. Solvable groups, like the Lamplighter group, do not have polynomial growth. Only the virtually no-potent groups have polynomial growth. Okay, so this is one theorem that illustrates this principle. Another theorem we mentioned is a theorem of Gleason and Yamabe, related to Hilbert's fifth problem. So now we're in the continuous setting. This is a statement about discrete groups, finitely generated groups. There's an analogous statement for continuous groups where the analog of polynomial growth is that of local compactness. So it says that every locally compact group is a generalized Lie group. I'll define this term in just a minute. Okay, so and this is closely related to Hilbert's fifth problem, which one formulation of which is to classify all topological groups that are locally Euclidean. That if you have a topological group that looks locally is homomorphic to a Euclidean space, does it have to be a Lie group? And the answer is yes. And it's proven using almost the same machinery used to prove this theorem here for locally compact groups. Okay, so you know what a locally compact group is. It's a topological group, Hausdorff, and locally compact. Right? It's got lots of open compact neighborhoods. Okay, so you know, a basic example of a locally compact group is a Lie group. Any finite dimensional Lie group, such as GLN or any other linear group, is certainly locally compact. A generalized locally compact, a generalized Lie group, it's a little bit like a virtual Lie group, but it's a bit more complicated. So the formal definition is that a group G, topological group, is generalized Lie if for every open neighborhood U of the identity, there exists an open subgroup G prime of G and a Lie group L and a continuous homomorphism phi from G prime to L, so that you can model most of G, an open subgroup, which is a big piece of G, can be modeled by a Lie group in such a way that the representation is pretty faithful in the sense that its kernel lies inside this neighborhood. So inside any neighborhood of the identity, you can find basically a normal subgroup inside U, such that when you quotient it out, what you get is a Lie group. More or less equivalent definition is that a generalized Lie group has an open subgroup, which is an inverse limit of Lie groups. I think that's equivalent in the metrizable case or something. Okay, so this is a bit of a complicated definition. Maybe I'll just give one example. So an example of a locally compact group is, of course, the circle. But you can also take a very small circle, a very short circle of tiny size that's still locally compact, and then you can take a product of these guys. So you can take a sort of infinite dimensional torus, but of increasingly shrinking dimensions, and you put some reasonable metric on the product, then this will be a locally compact space. It's not a Lie group because it's got this infinite dimensionality in it, but you can quotient out. Sorry, if you quotient out by the tail of this big infinite torus, you can quotient by a really small subgroup, and the quotient would be a Lie group. And so this thing, it's not actually a Lie group, but you can quotient out by arbitrarily small subgroups, and they'll become Lie. Okay, and basically. The Gleason-Yamabe theorem is that all locally compact groups are like this. Now, it's not really obvious that these two things are related, but actually Gromov's original proof of Gromov's theorem uses not quite this theorem, but a closely related theorem, also related to Hilbert-Smith problem, and he used that to prove in this proof of Gromov's theorem. And then very recently, in fact, last week actually, okay, so Ben Green, Emmanuel Briard, Tom Sanders, and myself, we proved a variant of these two results, which we'll call the non-commutative Feynman theorem. So Gromov's theorem was about discrete groups, Gleason-Yamabe is about locally compact groups, and our theorem is about finite approximate groups. I'll have to find this term in a minute. Is controlled by a virtually nilpotent approximate group. Okay, so let me explain some of the terms here. Okay, so for us, an approximate group, so a group is a set of elements with some multiplication operation, which is symmetric. You can invert it. It's got the identity, and is closed under multiplication. So an approximate group is the same thing, except that instead of being actually closed under multiplication, you just almost close under multiplication. So for us, an approximate group is a subset A of an actual group which contains identity. It's symmetric, so if you're in your set A, then your inverse is in the set A. And then when you take the product set of itself, these are all the products, you don't get back A. If you did, then you'd actually be a group. But you say that to be an approximate group, actually let's say a K approximate group, where K is a parameter. To be a K approximate group, the product set has to be covered, can be covered by K left translates. Okay, so you can find some elements, G1.A up to GK.A that cover the A.A. It's like bounded doubling. Okay, so what are examples of approximate groups? Okay, so for example, actual groups. All right, so groups. Any group is an approximate group with K equals 1. In the abelian case of arithmetic regressions, let's say in an abelian group. So a set like A plus R plus 2R. Oh, actually symmetric. Okay, so maybe not this, but let's say minus NR, R0, R up to NR. So an arithmetic progression centered at the origin that contains the identity, which is 0, is symmetric. And if you now take a sum set now, the sum set of this progression is about 3 times bigger. You can cover it by about three translates of the original group. So it will be a 3 approximate group. Another example is discrete balls in an abelian group. It's a more general version of this progression example. If you look at ZD, say, and you take some big ball, maybe say a Euclidean ball of radius r, a Euclidean ball centered at the origin, then this is symmetric, contains the origin, and when you add it to itself, you get a ball of twice the radius, and if D is bounded, you can cover that by a bounded number of copies of the original ball. Okay, and you don't have to take a Euclidean ball. You can take any other ball in any other convex metric, like a box, for instance. Very similarly, you can take a discrete ball in a nilpotent group, and you get a very similar object. So, for instance, you can take all the elements in this Heisenberg group, where this entry is between minus r and r, this entry is between minus r and r, this guy's between minus r squared and r squared, and you can check that will also be an approximate group. Okay, you can discrete balls in an nilpotent group, also small balls in a Lie group. This is now a continuous example of an approximate group. If you have a Lie group, for example, UN, unitary group, is the identity. If you take a small ball of some, say, radius, so like all the unitary matrices of distance between R to the identity, that's symmetric and is the origin. If you define, let's say, Hilbert-Schmidt norm metric, doesn't really matter. And then if you look at its product set with itself, you get a ball of radius about 2R. And again, if your dimension is bounded, you can cover that by a bounded number of copies of your original set. So that's another example. And then you can start combining. So just like in Gromov's theorem, you can combine nilpotent groups and finite groups to get virtually nilpotent groups. You can combine the example of, let's say, discrete balls in a nilpotent group and finite groups to get what you might call virtually nilpotent approximate groups. So the way these work is that you have a group G, which is an extension of a nilpotent group by a finite group. So the way I think about this is that you have a nilpotent group downstairs here, a nilpotent group, and then above every point you just somehow stick in a finite group H. And there are various ways you can do this, and like a semi-direct product or something. Okay, and then you get this finite extension of this nilpotent group, and then you can take a ball down here, an approximate group down here, and then pull it back to. So you have a little ball down here. You can pull it back to a set like this. You sort of thicken your ball by blowing up each point into a finite group. And if this guy was an approximate group, you can easily check that its image upstairs will also be an approximate group, just from the fact that it's a homomorphism. And that's a more general example of an approximate group, which is analogous to the virtually nilpotent groups that show up in Gromov's theorem. And our theorem is that these are basically the only finite approximate groups out there, actually. That every finite approximate group in any group comes from a virtually nilpotent group, is controlled by. Now, what does controlled by mean? It's just a technical definition. We say that one set A is controlled say K controlled by B if A is pretty big. Let's say these are finite sets. In a group. see that one finite set in a group controls another if A is pretty big, let's say it's bigger than B over K, but also A can be contained in, is covered by K left or right translates. Of B, so that you can find K left translates of B that cover A, you can also find K right translates of A that cover B. So for example, in ZD, if you take a ball of radius R and a cube of length R, these sets control each other. Okay, so it's very much like the notion of an equivalent norm in finite space geometry. Okay, and so not every approximate group is actually a ball. I mean, for example, you could take a ball and just cut some holes out of it, get some Swiss cheese, and as long as you don't cut out too many holes, that will still be an approximate group, but it's no longer a ball, but it is controlled by a ball. Right? It's covered by a ball which has a size about the same size as that original set. And so up to this sort of bounded error, every finite approximate group is actually controlled by a virtually unipotent group. This is not quite the formal statement of the theorem. There's always k's. Actually, every k approximate group is k prime controlled by a virtually unipotent group where k prime depends on k. I don't want to write down these sort of extra details. Okay, so these are the sort of theorems that illustrate this principle. And I was going to talk about proving at least one of them, but actually I don't, rather than actually talking about any one of these in detail, I want to talk about the connections between these theorems, and also some other theorems that connect these. So, as I said, Gromov's original proof of Gromov's theorem used something, a close relative of the Gleason-Yamabe theorem, and in fact, our proof of this theorem also uses actually the Gleason-Yamabe theorem as well, although you can use a weaker version, but you have to use something like the Gleason-Yamabe theorem, at least so far. Okay. So there are some connections between these. So this is a statement of finitely generated groups of polynomial growth. This is a statement about locally compact groups and a statement about finite approximate groups. They are connected to each other. So, for example, in a locally compact group, have lots and lots of approximate groups. Every open symmetric pre-compact neighborhood of the identity is an approximate group. Okay, if you have a locally compact group and you take some open neighborhood which is pre-compact, so its closure is compact, then and is symmetric, then if you multiply with itself, you get a slightly bigger open set, but it's still pre-compact. Okay, compact times compact is compact because multiplication is continuous in a topological group. So the product set is contained inside a compact set, and so you can cover it by a finite number of translates of your open set A. And so so you will be an approximate group for some k, for some finite k. So that's one connection. Locally compact groups have lots of approximate groups. Conversely, the way we actually use this theorem to prove things about finite approximate groups is that we have a correspondence principle. Okay, that given a sequence AN in GN of finite approximate groups, there's a way of taking a limit that you can take. There's a way of taking a limit of these different finite approximate groups which can live in different groups. And there's a way of taking a limit which gives you a new object A which lives inside, which will now be a continuous approximate group inside a new object G. And G will be a locally compact group. And A will be an open pre-compact set. And the properties of A, N, and Gn are sort of the asymptotic properties of A, N, and Gn are very much tied to the properties of A and G. So I won't describe this correspondence, maybe I will have some time later, but I just will give an example to sort of illustrate the type of thing that you should keep in mind. So, for example, suppose you're working in Z2, and approximate groups, find approximate groups of uniform doubling with uniform K. Yeah, so they have the same K. So if you're in Z2, for instance, you can take a box of size R, say box of size 2 to the n by 2 to the n. Okay, so you take a big box and they get bigger and bigger, and I call this A sub n. Okay, so these are boxes that are getting bigger and bigger in this discrete lattice, or equivalently, you can rescale them. You can think of them as actually unit square boxes in a very fine lattice. That's probably a better way to think about it. You can take the Z2, so squash it down by, scale it by a factor of 1 over 2 to the n, and then your AN is like this discrete unit square, and the unit square is getting finer and finer as it gets bigger, and it turns out that you can extract a limit, and what the limit looks like is it looks like a unit square in R2. Okay, and you can sort of see intuitively that the unit square is in some sense the limit of all these discrete things, and there's a way to make this type of thing precise. And this is one thing that we do. And it turns out that, in fact, more generally, given any sequence of approximate groups where the constant k of the approximate group is bounded, you can always find a limit which has this comes from a locally compact group. And this is how we connect these two. And then finally, why is polynomial growth connected to these other two categories? And this is just the pigeonhole principle. So this is an observation that if G has polynomial growth, then if you look at the ball of radius R, all these balls will be approximate groups. For many radii R. You see, as R increases, all these balls they keep increasing in size, but they can only grow polynomially. They can't grow exponentially, and so because you have polynomial growth, you can show that so just by the pigeonhole principle, there are many R's for which, for example, the ball of radius say 4R, we bounded by some constant times the ball of radius R. Okay. If you make the ball 4 times bigger, you can't keep doubling by a constant because that would give you exponential growth and you want polynomial growth. So there are lots and lots of balls which give you bounded doubling, and so and once you have that, you can show just by some covering arguments. If you have this, you can easily show that this is I think a ball of radius 2R will then be an approximate group once you have some sort of bounded doubling like this. Yes, this implies. Okay, so you can find many balls for which you have an approximate group, and then you can start taking these limits, and you can extract out these locally compact groups, or actually more precisely, the way Gromov does it, you get locally compact metric spaces, and your group acts on those spaces. You actually get an action on a locally compact space rather than a locally compact group, but very, very similar nevertheless. Okay, okay. So there's always connections here. Let me write down some other theorems that are also closely related to these 3 theorems here. And they're used in the proof of several of them. Okay, so some other theorems which are related. There's a theorem of Jordan, which you actually heard talk about by Emmanuel on Wednesday. So now this is the context is in linear groups. Every finite linear group, so a group that's contained inside, say, GLN over the complex numbers, every finite over C, is virtually abelian. So it has a finite index subgroup which is abelian, Now, the way I've stated it, this is trivial because you're already finite, so of course you're virtually anything. But the key point is that with bounded index, okay, that the abelian group is actually most of the finite group. The index actually is bounded depending only on the dimension. That's Jordan's theorem. Okay, then there's also the Tits alternative, which is a similar sort of thing, that instead of a finite linear group, if you have a finitely generated linear group, again over C, there are versions of other fields, but this is what we're going to see, which have no free group, with no free subgroups. So no subgroup that generates the free group on two generators. It won't be virtually abelian, but will be virtually solvable. And conversely, once you're virtually solvable, you can't actually have any copy of the free group. So you have one or the other. This is the Tits alternative. And then another theorem in the same spirit is, okay. So the Kitaev theorem, if you now have a finitely generated group, in a semisimple group, in a compact semisimple group, such as, actually a good example is UN, such as the unitary group, which is dense. Every group which is dense is very dense. So dense in the topological sense, that every element in your group is close to an element in your finitely generated group. So yeah, okay. So is very dense. And what that means is that every for all R, every element in the big group, let's say UN, lies exponentially close to an element of G, lies within exponential of minus R to a small constant of an element of the ball of radius R. So if you take the balls of radius R in your dense group, they will fill out this group, but in fact they will fill out the group very, very rapidly. After R steps of making a ball bigger and bigger, you can actually get close exponentially close to any point in your group. This implies in particular your group is growing faster than polynomially. So you have very rapid growth. So this is sort of a contrapositive of the other sort of statements that so if you're sort of very non-finite in the sense that you're dense, then in fact you must grow very, very, very rapidly. And then finally, there's one other related theorem, much more classical, on chronica. So this is a theorem that says that is about the dynamics of linear matrices. If you have a matrix which is invertible with integer coefficients, and it has polynomial growth, so that if you raise it to higher and higher powers, if these matrices only grow polynomially, so like the size of the coefficients only grow at a polynomial rate, then T can't be very complicated. Then T actually has to be virtually unipotent. Then, in other words, if there's some power of T, say T to the M, is unipotent. That always eigenvalues are 1, or if you subtract 1, it becomes nilpotent. For example, an upper triangular matrix. If you raise an upper triangular matrix to higher and higher powers, then the powers only grow polynomially. And this is saying that that's basically the only matrices that do that. Okay, there's also like matrices that rotate. Rotation matrices also, like reflections or something, will also grow polynomially. But these are the only matrices that grow polynomially. This theorem is actually a special case of Gromov's theorem. saying that this t-square polynomial is the same as saying that if you take a semidirect product of z acting on zn using t, that if that group goes polynomial, then it's virtually nilpotent. That's equivalent to the statement here. Kronecker did not phrase this theorem like this. He phrased it in an equivalent form, which is that if an algebraic integer has all Galois conjugates on the unit circle, then there's a root of unity. Okay. But yeah, if you just use a Jordan decomposition, you can see that these two are actually equivalent statements. That if you have a matrix of integer coefficients, its eigenvalues are all algebraic integers, and you can just play around and you see that you get this. Yeah, and so in fact, Kronecker's theorem is used to prove certainly Gromov's theorem, and probably, yeah, these are all interrelated. I think the Tits alternative uses Jordan's theorem and Kronecker's theorem. Gromov's theorem uses Jordan's theorem and the Tits alternative. They're all tied together. I forget exactly how they connect. But you can see this is also in the same spirit, that when you have controlled growth, you get some sort of nilpotent type structure coming out. So the way you prove these theorems, they all use each other, but that's not the end of the story, because you have to start somewhere. All these theorems actually, I mean, they're all different. They all have several proofs by now, but they all have some features in common. All the proofs are based on some sort of induction of dimension. So in each one of these problems, there is some notion of how big your group is. In a locally compact, in a finite approximate group, we have this parameter k, and k is a doubling constant. It's not quite a dimension, but you can use it to define things like dimension. In Gromov's theorem, you have an order of growth. That order of growth can be taken as a kind of dimension. If you have a locally compact group, there are topological notions of dimension based on how easy it is to disconnect your group. There's another notion of dimension which is actually called height, which is that you can take a group G, locally compact group G, and you try to find inside it a normal subgroup, G1, such that its quotient is big, it's non-compact. And then you try to find inside that guy another normal subgroup, such that this quotient is also non-compact. Okay, so for example, you might have RD. So inside it has got RD minus 1, and the quotient is non-compact, and then inside it's RD minus 2, and so forth. And you can try to keep doing this, but you'll find that if you're locally compact, you can't keep doing this forever. That there's a bound as to how deep you can go. Somehow it's for the same reason that infinite dimensional spaces just don't tend to be compact. Unit balls don't be compact. And so there's notions of height like this, which you can show to be bounded. And so you try to induct on some sort of dimension. You assume that you can already prove these theorems for lower dimension. And the strategy is always to try to split your group. Okay, so if you start with your original group G, which could be one of these three things, your strategy is to try to find a splitting. Okay, so you try to find a representation of G in some other group H, which has some kernel K, where one of these guys is very well structured. Something you understand, such as an abelian group, or a linear group, or something, or solvable, something that you understand pretty well. And also somehow non-trivial in some sense. And if it's non-trivial enough, then the other factor we have lower dimension. As long as if one factor is somehow big enough, the other factor will then have to be smaller. For instance, if you have a group G sitting above some group H of kernel K, okay, like if this is a group which has polynomial growth of some growth D, and H is already non-trivial, if H is infinite, if you have an infinite group, then balls of radius R have to grow by at least R, okay, just because each ball has to discover a new element of the group. And so if balls of here of size R to the D and balls here of size at least R, it's not hard to show that therefore that balls in the fiber K can only grow by at most like R to the D minus 1. There's a reduction in growth order. And there are similar things you can do in these other contexts. And so once you actually have a non-trivial splitting, so you either have a non-trivial representation or you have a non-trivial normal subgroup that you understand. Then you have a sequence. The other factor has lower dimension, so you apply the induction hypothesis, and so you get your no potent or whatever structure on it, and then you have to glue the two guys together. Like gluing is not always trivial, but it's relatively straightforward. So the hard part is to find either a structured guy on the right or a structured guy on the left in all of these problems. And so okay, and so we know of a couple ways to do that now. The simplest example of this is a Jordan's theorem, that every finite linear group is virtually abelian. So here the strategy is to actually look at to find a good element inside G. So for example, to prove Jordan's theorem, the key observation is actually Emmanuel mentioned it on Wednesday, is that if you have two elements, if you have two unitary matrices, and they are close to the identity, so they're if you have two elements that are already close to identity, then they almost commute, in the sense that their commutator, which is GH with H inverse, will be even closer to the identity. Okay, and this is actually a very simple computation. Is that if you want to measure how close the commutator is to the identity, you can factor this. This is actually the same as a G minus 1, H minus 1, minus H minus 1, G minus 1. That if you just work out these two products and subtract them, and you play around with the fact that everything's unitary, and you take some reasonable norm, such as Hilbert-Schmidt or operator norm, okay, you have this identity. And then as long as it's a reasonable norm, you just use the triangle inequality, and you get something like this. Okay, so if H and G are close to identity, then the commutator is even closer. These are like epsilon close, and this is like epsilon squared close. They're even closer. So this is a basic observation, and it powers a lot of these proofs here. And so one corollary of this is that if you pick the element of your group which is closest to the identity, so if you have a finite group, so one corollary of this is that if G is the closest non-trivial element to the identity, okay, so you have a finite group, okay, and you pick the element which is closest to identity, then this guy will commute with almost everything, and G will commute with all elements of G that are reasonably close, are fairly close. To 1. Okay. In fact, any H which is closer than 1/2, distance 1/2 to the identity, if G is the closest element to 1, then this guy, the distance to 1, it will be less than. Yeah, so this would be strictly less than G minus 1 if H minus 1 is less than 1/2. And so if G is the closest non-trivial element to the identity, this can only happen if this commutator is trivial. And so you see that the closest element must actually commute with a very large portion of your group, all the elements which are inside the ball of radius 1/2 at the origin. And so what you found in the picture I had before, so inside this group, you found this little group element, which of course generates some subgroup K. So you find some non-trivial central subgroup of well, maybe not of all of G, but maybe a slightly smaller set G, which is the set generated by this smaller ball. But there was this non-trivial subgroup which is centralized by a lot of your original group, and you can quotient it out, and you get something smaller, and you can keep going from there. And this is basically all there is to know about. I mean, the modern slick proof of Jordan's theorem is basically it's almost done at this point. The Solovay-Kitaev theorem is also done in a very similar way. You get some preliminary approximation. Every element can be approximated in some lousy fashion by an element of your finitely generated group, but then you can take commutators and make the approximation much better, and you just keep going, and you can get something like this. Okay, so this is one thing that we can do, but it relies very much on having some inequality, some commutator inequality like this. And if you're already in a unitary group, you can do this, but if you don't have a unitary group to begin with, it's not obvious they can actually set this up in the first place. So this is one tool. The other tool we have is to work on the other side. So rather than find nice K's inside your G, you find nice H's on the other side. So the other main tool we have is we want to find good non-trivial representations, linear representations. So you have your group G, you want to understand it. If you can find a good linear representation, then you have mapped a linear representation. It's just a way of mapping G into a linear group, and it has some kernel. And as long as your representation is not entirely trivial, so it doesn't just all map to 0, then your image will be something non-trivial here, and that will make K smaller, and you can work with this. In particular, if you can get a representation into the unitary group, then you can start playing, you can use Jordan's theorem, and you can get a lot of mileage out of that. So, so a lot of focus in proving things like Gromov's theorem has focused attention on trying to get linear representations, trying to take an arbitrary group and give it linear structure. And there's two ways we know how to do this. So one way is sort of the Gleason-Yamabe way, which is that if you have an arbitrary locally compact group, how do you get a linear representation? The idea there is that if you have an arbitrary Lie group, every Lie group has pretty much has a natural linear representation, which is the adjoint representation. If you have a Lie group, then every Lie group comes with a Lie algebra, which is the tangent space of the origin. And your group G conjugates the elements of this Lie algebra around. And so that gives you a way to represent elements of G as linear transformations on this finite dimensional space. And that gives you a useful linear representation. And it turns out with a lot of effort that you can do the same thing for locally compact groups. That if you have a locally compact group, you can define a tangent space. So I mean, what is a tangent vector? I mean, it's the tangent vector is basically the generator of a one-dimensional subgroup or one-parameter subgroup of your Lie group. And so in a locally compact group, there is also a notion of a one-parameter subgroup inside your group G. You can define such things, and you can show with a fair amount of effort that these things exist and that they form a vector space, and your group G acts on them, and it gives you an interesting representation. These are all actually reasonably hard things to show, but once you have that, you actually get a linear representation. And this is a key component of the proof of things like Hilbert's fifth problem. So this is one technique, and then the other technique we have is to use spectral theory and work with special functions, eigenfunctions of various operators. So the other way to get representations is to work with eigenspaces of so to let G act eigenspaces of somehow interesting operators. So okay, of nice operators. So this, for example, was done by Bruce Kleiner about a few years ago, where he gave a new proof which was much more quantitative of Gromov's theorem. They didn't have to rely on this whole Hilbert-Smith machinery, which is quite difficult. So what he did instead was that he took a finely generated group, which sort of looks something like this. So you have a finely generated group. You can think of it as a Cayley graph, as an infinite graph where two group elements are connected if there's a generator that moves one to the other. And so you have this Cayley graph, and it defines for you this Laplacian. So if you have a function, a complex valued function on your group, you can define the Laplacian, which is basically the difference between your value of function and the value of the surrounding point. So this is a slight oversimplification, but basically, if you take a function and you compare it with the average of its neighbors, and that difference you want to call Laplacian. Actually, this is not quite the right definition, but just to oversimplify a little bit. So this is you can define discrete Laplacian, and you can show that if you have a group of polynomial growth, then this Laplacian has got a lot of eigenfunctions which have very small eigenvalue, and then you can take a limit, and you can actually construct non-trivial eigenfunctions with eigenvalue 0. So you can show that there exist non-trivial harmonic functions. So functions where each point is equal to the value of all its nearby values, and so they're not constant. That's what non-trivial means, but they don't grow too wildly. In fact, you can make them Lipschitz. So a good example is that if you're working in say ZD, the standard generators, then any coordinate function is a harmonic function. It's the average of its nearby values. And in fact, in that particular case, those are actually the only harmonic functions. They generate the entire set of harmonic functions and the constants. So you can use some abstract spectral theory nonsense to get non-trivial harmonic functions. And so you have this space V, space of all Lipschitz harmonic functions. Now let's say quotient by constants. So this is non-trivial space. And then the thing is that if you have a harmonic function and then you shift it on the left by a group element G, if you multiply G, if you multiply shift F on the left by some element like H, it's still harmonic. So this space is acted on by G. And so you actually have a non-trivial representation of G acting on the harmonic functions here. And once you have that, you have this linear representation, you can then apply all this theory of linear groups that we know. So Jordan's theorem, Tit's alternative, you can use all this stuff. And you can start splitting your group and getting things of smaller growth. And once you have this, you're done, except that there's one thing you have to check, which is that this is a space of harmonic functions. The problem is that this space may be infinite dimensional, in which case your representation is useless. And so the hard part of Kleiner's argument, in fact most of his paper, is devoted to showing that that if G has polynomial growth, then the space Lipschitz harmonic functions is finite dimensional. Now, this is actually related to, so in complex analysis, you have Liouville's theorem. It tells you that on the complex plane, every bounded harmonic function is constant. But Liouville's theorem also tells you that if you have a harmonic function that grows linearly, then it actually has to be a linear function. That there's only a finite dimensional number of possible harmonic functions. And if it goes quadratically, then it has to be a quadratic polynomial, so on and so forth. And you can prove that by, I think, like Cauchy integral formulas, the standard proof. But it turns out that you can adapt that proof. I mean, of course, we have nothing like the Cauchy integral formula for this. But it's actually the same sort of principle. The reason this works is because of what's called elliptic regularity. If you have a function which is harmonic on a big ball, if you have a function which is harmonic and it fluctuates, let's say it's how should I say? Yeah, if you have a function which is harmonic on a big ball, then if you look at what happens at a much smaller ball, then what normally happens, as long as you have polynomial growth, if you have polynomial growth, then you can cover the big ball by finite many copies of a small ball, and so the volumes of these balls are sort of comparable. That every time you have a function which is harmonic on a big ball, it becomes very smooth on a smaller ball. That roughly speaking, you can show that the variation, if U is harmonic, then the variation of U on a small ball is a lot smaller than the variation of U on a big ball. And there's various ways to make this precise. You can talk about like mean square fluctuation. You can take U on a big ball, subtract a constant, look at the mean square, and take the integral or C. And that's a measure of mean square oscillation, and you normalize it correctly. But the mean square oscillation on a big ball controls the mean square oscillation on a smaller ball, that you have less oscillation. And you can prove this by lots of integration by parts or summation by parts in the discrete world. The key word here is reverse Poincare inequality. Okay, it's a variant of the fact that harmonic, the harmonic function is always smooth, and you can prove that by integration by parts, and that proof actually works verbatim pretty much in any group of polynomial growth. And so you can show that that a harmonic function on a big ball has less fluctuation on a small ball than it does on the big ball, which means that actually you can one consequence of this is that if you cover your big ball by lots of small balls, that you can control that your harmonic function on the big ball is almost completely described by the mean value of your function on little balls like this. That given your function on your big ball, you average it on these little balls, you get all these numbers, and those numbers essentially capture most of the information about your harmonic function. And the more precise way to say that is that if you look at the kernel, if you look at all the harmonic functions which have mean 0 on each one of these balls, you can show that set, the dimension of that space, is less than, say, half of the dimension of your entire set of harmonic functions. And then from linear algebra, that gives you a bound on how many harmonic functions there are in terms of how many balls you need, small balls you need to cover the big ball. And in a group of polynomial growth, that's bounded, and that gives you a boundless dimension. And that's the key to Klein's theorem. So it'll be nice to understand this particular trick more carefully. There are other places where you use the spectral theorem and you take some nice function and to get non-trivial representations. The proof of the Peter-Weyl theorem is also another example where this type of trick comes up. If we could understand this a lot better, then we would have better proofs of these other things too. The non-commutative Feynman theorem, right now we can only prove it through this Gleason-Yamabe machinery, which is actually kind of hairy. It would be nice to have a proof like this. We're still working on that. Okay, I'm out of time, so thank you very much.
So,
correspondence principle you mentioned for approximate groups, is that a sort of abstract nonsense typical argument, or is there something?
It's mostly abstract nonsense, yeah. So it uses an outer product. Yeah, so the yeah, so but it does use one combinatorial lemma, which was discovered independently by Sanders and Krupp-Sissak. So the I mean, one of the defining features about locally compact groups is that every time you have an open set U, you can find inside it a smaller open set V, such that V times V is contained in U. Right? From the basic, that's almost the defining axiom of a topological group, actually. And so there's an analogous statement. It's an analogous statement in approximate groups. You have an approximate group A, then you can find a small set S such that you can raise it to whatever part you like, S to 100, and it's still contained inside. Well, not quite A actually. It leaks out a little bit A before, right? But you can find lots of little small balls inside your big ball, and you have some control on how big these balls are. So if you have a sequence of these approximate groups, you can take an outer product, and you get now this enormous infinite approximate group, but it will still have inside it lots of these other these smaller subballs, and you can use that to make a base for a topology or a metric if you like. It won't quite be Hausdorff. There'll be this kernel of like all the infinitesimal elements inside here, and you have to quotient that out. But once you do that, what you get is shown to be a locally compact group because it's totally bounded. You can cover this big set A by finding many copies of the small set S, and so you get total boundedness over here. You get completeness for free because outer products are also countably saturated. There's this logic. There's this nice little property in logic that also helps you for free, and then you just use Heine-Borel and you get local compactness. And that's where the principle comes from.
Any other questions? I was going to say maybe you could hint at the differential geometry application. Take a while.
Okay, yeah, so one of Gromov's motivations for studying this, for proving this theorem, was to analyze Riemannian manifolds. And so he had this nice application of his theorem, which is that, that M is a compact manifold. And its Ricci curvature is always non-negative, so it's a positive curve, think of it like a sphere. Then one consequence of positive Ricci curvature actually is that balls in your manifold grow at a polynomial rate. Actually, more importantly, balls in the universal cover also grow at a polynomial rate. This is part of what's called this consequence of what's called the Bishop-Gromov inequality. And you can use that, and you can apply Gromov's theorem, and you can conclude that G has a virtually important fundamental group. Okay, so somehow manifolds of positive curvature are not too crazy. Okay, I mean they can have a little bit of topology, but not so much that the fundamental group goes wild. It has to be very super important. As a consequence, yeah. So one of the consequences of this theorem that we proved last week actually is that we can actually strengthen this a little bit. That there exists a little epsilon, which depends only on the dimension, such that if your Ricci curvature is actually bounded from below by it's slightly negative. These are almost non-negative Ricci curvature manifolds. Then, as long as it's small enough, you still have the same conclusion. Because we can still localize Gromov's theorem to a single ball rather than having to deal with the entire family of balls. Yeah. So that's a little application.
Okay, well, please join me in thanking Terry again.